Well, hey there. It's time again for another podcast. This one's going to be pretty brief. It's on matter. And if you hear a little kitty cat in the background, just start laughing. His name is Mooch. He's very cute. I may put a picture of him up here at the end of it. So let's go ahead and get started. We're going to talk about matter. Those of you who are in my class have already worked with some hypothetical matter in the form of nuts and washers and bolts and classifying it. So that's kind of where we're going to start. So we have classifying matter. You may classify it as either a pure substance or as a mixture. Pure substances are those that are made of either elements or compounds. They can only be those two substances, elements or compounds. A mixture is not chemically bonded as an element or a compound might be. A mixture, rather, is a physical mixing of two or more elements, or element and a compound, or two or more elements and compounds. Either or any of that will work. Okay, so when we talk about mixtures, we generally classify them as being either homogeneous or heterogeneous. Another name for a homogeneous mixture is a solution. And when we talk about a homogeneous mixture, what we're talking about is the fact that it is uniform throughout. That means you can take a sample of a homogeneous mixture from any part of that particular example, and it will be just like any other sample that you choose. An example of a homogeneous mixture would be, let's say, sodium chloride in water. When you put sodium chloride in water, the sodium chloride dissolves in the water. You therefore have sodium ions floating around and chloride ions floating around, and the concentration of sodium ions and chloride ions does not vary as long as it is indeed a homogeneous mixture, meaning you've not put in so much sodium chloride that you have a bunch sitting at the bottom, for example. That's known as a mixture holding too much of, in that case, the sodium chloride. It's called overly saturated. It's not super saturated, it's called overly saturated at that point. And if I were to take a sample of, say, ocean water and take a pipette full from the bottom of my container and from the top, what I would get is identical samples. However, in a heterogeneous mixture, as the prefix hetero implies, we have different throughout. It means that it is not uniform throughout. It means that you take a sample from, say, the bottom of a container and a sample from the top of the container, and you do not have a guarantee that they will be identical. They might be, but you don't have a guarantee that they will be identical. An example of a heterogeneous mixture might be dirt in water. You're going to have some at the top, some at the bottom that are not necessarily identical. Okay, so now that we've talked about mixtures in a decent amount of detail, let's talk about elements. And elements are classified as the simplest example of a pure substance. An element is made of atoms. Those atoms are all of one type of element. They're not necessarily identical. We'll get to that a little bit later, but let's just say for right now that when we have a sample of hydrogen, we have hydrogen atoms present. Now, hydrogen gets a little more complicated, as I'll tell you in just a moment. But if I have a sample of carbon, every bit of that sample of carbon is made of carbon atoms. If we have an element that happens to exist in different physical forms, those different physical forms are called allotropes. And I've given you an example here of the different allotropes of carbon. You might recall from previous knowledge that carbon can exist as diamond, graphite, or coal. And one you might not be familiar with is the compound, it's not a compound, the element Buckminster fullerene. It's an allotrope of carbon that contains 60 carbon atoms. So what I have on this slide is an example of 3 Buckminster fullerene molecules that are bonded to each other. They look like geodesic domes, which is kind of what the Epcot spaceship Earth looks like. And Buckminster Fuller was the designer of the geodesic dome. He was the one who, I guess, first proposed the geodesic dome. Since he did that, they honored him by naming this molecule Buckminster fullerene. And its common name, as you saw in the previous slide, is buckyballs. Pretty cute, huh? So they're little spheres of 60 carbon atoms that are attached to each other. And again, this slide shows you an example of Buckminster fullerene that has 3 different molecules. So the next type of pure substance is compounds. Compounds are when 2 or more elements actually bond to each other. So I'd mentioned that hydrogen was a little weird. The reason hydrogen is a little weird is because when hydrogen exists by itself in nature, it exists with 2 hydrogen atoms that are chemically bonded to each other. It's called a diatomic molecule. And you take that diatomic apart and it means 2 atoms are in each molecule. So you might have seen before that hydrogen is written as H with the subscript to the right of it of 2. There are 7 elements that exist in nature as diatomic molecules. They are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. I list them in that order because there's a silly little mnemonic device that is pronounced Brinkelhoff, which is taking those 7 elements and putting their symbols in that order. You get BRINCLHO, and F. It's nobody's name, it's just a cute little mnemonic device. Another way you can remember them is that there are 7 elements that are diatomic in nature. When they are by themselves, they are diatomic, and they form the number 7 except for the one goofy one that's hydrogen. So if you look on a periodic table at nitrogen, oxygen, fluorine, then go down chlorine, iodine, bromine, iodine, you will see that it makes kind of the number 7. You just have to remember that hydrogen's a part of it. Okay, so compounds are classified as being molecular or ionic. This is going to come up again and again and again in chemistry, so get this one straight in your head. If a compound is considered to be molecular, then it's made of 2 or more non-metals that are bonding to each other. If it is ionic, then it is typically going to contain a metal and a non-metal, though we're going to extend that definition once we get a little deeper in the course. The key thing is that ionic compounds are made of ions. So sometimes we will encounter ions that don't contain a metal, but for right now, let's just say molecular compounds are made of 2 or more non-metals bonding to each other, and ionic compounds are made of a metal and a non-metal bonding to each other. So when you look at a periodic table, you've got to be able to determine where the metals are and where the non-metals are. And I'll go over this in greater detail as well, but for the most part, the periodic table is made of metals. There are actually very few non-metals on the periodic table. And we'll talk about how to discern that a little bit later. Okay, so let's go back to the discussion of mixtures for a wee bit here and talk about what are known as separation techniques. I'm going to ask you to be familiar with 6 separation techniques. Those of you who have me for Chemistry 1 honors have already experienced some of these separation techniques. What I'm going to do for each is tell you why it works and then give you an example of a mixture that you could separate using this technique. So again, these are techniques for separating mixtures. You recall that mixtures are simply physical combinations of elements or compounds or any of that ilk. They are not chemically bonded. That's a key point here. That's why we can separate them using these physical means. So the first one I have up here is filtration. Filtration works because of differences in particle size, and occasionally we could say that that means differences in density. When you filter a mixture, what you're doing is passing small particles through some sort of sieve, some sort of mesh device, or something with holes in it, so that the small particles pass through, but the larger particles stay on whatever your sieve, mesh device is. Or in the case of those of you who are in my Chemistry 1 honors class, y'all did paper filtration. When you filter it, you end up getting the filtrate, which is what passes through the filter, and the particles that are too big remain on the filter themselves. So an example of a mixture that you could separate is, let's say, what you did in your lab in Chemistry 1 honors, and that was separate insoluble matter from a mixture of an analgesic in water. Remember, your insoluble matter ended up staying on your filter. You could certainly use as an example filtering, let's say, coffee grounds from a mixture of coffee grounds in water. Now the key thing here is that when you're giving me an example of something that can be separated using these techniques, you need to give me an example of a mixture that can be separated. You cannot just tell me that coffee can be filtered, because coffee actually is the filtrate. It's what is passed through the coffee filter paper. So it's not correct to tell me that coffee can be filtered. It is correct to tell me that coffee grounds can be filtered from the water that they are in. Okay, a second technique that I'd like to discuss with you is evaporation. Evaporation will work because of differences in boiling point. An example of using evaporation to separate a mixture would be having a mixture of sodium chloride in water and just letting it sit out, exposed to air, and eventually enough water will evaporate and leave behind the sodium chloride. Now, the problem with evaporation as a separation technique is you cannot retrieve both portions if there are indeed two portions of the mixture. So as in my example, if we're just waiting for the water to evaporate, then that means all we really wanted was the sodium chloride in that particular example. So it's not a great separation technique because it doesn't allow you full use of the components of the mixture. Alrighty, centrifugation is the next one that I have up here. And it works based upon the centrifugal force. Those of you who are Latin students, fugo means to fly, so centrifugation means to flee the center. Centrifugal force means center fleeing. Centripetal force means going toward the center. So centrifuge, which is a device used in centrifugation, works because of the centrifugal forces. So what a centrifuge does is essentially separate a mixture based upon differences in density. When you place a mixture in a centrifuge, the centrifuge then spins at a very high rate of speed. If you're in my class, I show you a centrifuge and show you how it spins. And the more dense part of the mixture will go to the bottom of the test tubes, typically what you're putting in the centrifuge, and the less dense portion will be at the top of the test tube. An example of a mixture you can separate using centrifugation would be blood. For example, you end up getting a pellet of red blood cells and platelets at the bottom of the test tube, and essentially you have water sitting at the top of the test tube. Alright, the next one is decantation, and decantation works based upon differences in density as well. It is a very simple process. It means that you will literally pour off the less dense portion of a mixture, and the more dense portion stays in, say, your beaker. An example of a mixture that is easily decanted would be dirt in water. If you let the dirt settle and then you pour off the water, you've separated the dirt in water mixture. Chromatography is the next one, and as its name implies, chrome means something about color. It's separating mixtures based upon colors. So I'm going to only give you one type of chromatography, and that's paper chromatography, because that's the only one we can do here at Caddo Magnet High School. I'm sure other high schools might have thin layer chromatography and gas chromatography units, but I certainly don't. So paper chromatography works because of differences in affinities for a mobile phase versus a stationary phase. And an affinity is a likeness. So it means that part of the mixture likes to move and part of the mixture likes to stay behind. It's based upon attractiveness of part of the mixture for the mobile phase or for the stationary phase. And a good example of what can be separated using chromatography is black ink. Some of you may have done this in middle school. We may end up doing a fun little paper chromatography demonstration here in this next week. But what you end up doing is just putting a dot of black ink on a piece of generally filter paper, and the paper is the stationary phase. You then dip the paper in water or some other solvent that acts as the mobile phase, because I believe we all know that if we dip a piece of paper in water, the paper will creep up the water. That didn't make sense. The water will creep up the paper, I believe is what I meant to say, and you'll end up seeing that all of your paper ends up getting wet. Just think about using those pH paper strips that you used. You noticed that it started creeping up towards your fingertip. So what it ends up doing with black ink is letting us see that black ink is not made of one color. It's made of many colors of ink, and the different colors of ink have different likenesses for that mobile phase, the solvent or the water, and they will be dragged up through the paper in the order of their affinities for the water. So the one that is most like water will be dragged out first, and subsequent ones will come out later. It makes essentially a ladder-like effect of colors of ink. And then the last one I have up here is distillation. Distillation works based upon differences in boiling point, which is how evaporation worked, remember. But the difference between evaporation and distillation is that in distillation we want to collect both components. So when we separate the mixture, we have the substance with the greater boiling point collected in a vessel, unlike with evaporation where water has the lower boiling point, so it went out into air, and then the one with the greater boiling point stayed behind. In distillation, we get to collect the one with the greater boiling point, like sodium chloride in water. The sodium chloride would be staying behind in a boiling flask, but the water would end up being retrieved in a different flask, so that we end up saving both components of the mixture. Distillation is a very widely used process. An example would be, of course, taking salt water and you get from it the sodium chloride and the water. And I have on the next slide a picture of a simple distillation apparatus. If you look closely at it, you see that there's a flask sitting on a hot plate that contains whatever the mixture is. It is heated. The top of that flask is closed to the environment and connected to what's known as a condenser. The kind of horizontal glass tube that's coming off is known as the condenser. So in this case of sodium chloride and water being heated, the water has the lower boiling point. It will rise as steam, try to exit the flask that's being heated, but it can't go through the top, so it goes out through the condenser. The condenser has two hoses connected to it that run cool water around an inner glass tube. Condenser's made of two glass tubes, one small glass tube surrounded by a larger glass tube. Well, that cool water that is flowing around the small glass tube takes the steam that has entered it and condenses it, as its name is implying it does, into water. And then that water drips out into the receiving flask that you see. Now, the last slide that I have here is a picture of a fractional distillation apparatus. You see that you have your hot plate at the bottom right-hand corner, and it looks a little different because there's that large column sitting above the flask on the hot plate. That's known as a fractional distillation column, and it has beads essentially in it that end up slowing down the distillation process. So the vapor that is going up that tube with the glass with the beads in it ends up slowing down the distillation process, and what it enables you to do is separate mixtures that have boiling points that are very close together. This is essentially what you see at an oil refinery. It's the same concept. Crude oil has so many different components in it, and their boiling points are pretty close together. So what you do is fractionally distill them, and you end up getting all of the components of the crude oil out. The first thing that comes out is methane. The next thing that comes out is probably ethane, and so on and so on. We go to heavier and heavier compounds and those with greater boiling points. So what you end up having at the end of a fractional distillation is of crude oil is really tar at the bottom. Now you might hear kitty cat meowing in the background. It is not Mooch. It is the other kitty cat. It is Lyndon. Mooch is currently on my shoulder, and Lyndon is outside listening to me talk and is very confused that I'm talking to the computer, so he is talking through the window outside. I apologize if you can hear that. I'll just have to put up pictures of both kitties now. Alrighty, again, I told you this one was going to be pretty brief compared to the first one for this year that was 48 minutes. This one's pretty darn cool, yeah? Okay, hope that helps you a little bit. This is pretty easy stuff at this point, but I promise you it will get a little more challenging. Okay, hope you enjoyed pictures of my kitties that I'll put.